So you can see my screen, right?
Yes, sir.
I need to, yeah, we need to begin with this, um, the point which was the concluding remarks. So yesterday we learned, at the end, we learned what we call the conditional distribution. Yeah. So the good thing about the conditional distribution was whether you have a discrete random variable or continuous random variable, in both cases, the conditional distribution, which is the PDF or the PMF, depending on whether it's discrete or continuous, it will always be the joint distribution divided by the marginal distribution. And of course, the denominator must be positive. And if you swap x and y, yeah, then the denominator has to be. So the reason he has given you these two formulas, that you need to remember that this distribution has to be tied to the second variable, and this distribution has to be tied to the second variable as well. I mean, when I say second, I mean the conditions, yeah. So actually, x is the first variable, y is the second. Here, the first variable is the conditioning one, so it's the marginal distribution for the first one. Here, the second is the conditioning one, so the marginal distribution is for the second one. Um, and as I told you earlier, it is always a good idea to use this in the subscript. You might say, okay, oh, I know this small y is a value of capital Y and small x is a value of capital X, so I should not need this. That thing breaks down when I substitute specific values. So let's say if I choose 1 for x and 2 for y, so I will have 2 given y. When it is 2 given y, I have no way from these two numbers whether this is the value of x or y. I have to look elsewhere. And I mean, if you just look at this formula, you have no way. So this will always be safe, right? Because you never substitute the random variables with their values, their functions. Okay. Now, why are conditional distributions useful? You can answer questions of this form, which we will do today. So conditioned, I mean, if I remove this condition, right, there is no condition. So you know how to compute probabilities of this form. All you have to do is to add, because the variable is x, so you take the PMF of x and you say, okay, add it over all possible values in the question. But if you now change that to a conditional probability, then you cannot use the unconditional PDF. You have to use the conditional PDF, and that is why it is this x means that the PDF is for x, and this y means that it is conditioned on y, and you still add over all possible values. So that's the utility of a conditional distribution. And if it is for a continuous variable, you can ask similar questions, but this time you will use integration rather than summation, but the integration must be of the conditional PDF. And this is an abuse of notation, because for continuous random variables, you don't write y equals y. What you mean by this is that y is in some tiny interval, right? Y plus dy. Yeah, but instead of writing this horrible thing, we simply write y equals y. Yeah. You can even replace this with this approximately equal if you are troubled by the inequality. And although this chapter doesn't say anything about that, but we can also use this formula to express the CDF. What will be the CDF here? Can anyone guess what will be the CDF? So it will be capital F x comma y of xy. You have to add all the, before that you need to express this as a probability, right? Let's write this on a separate page. So let me remove all the annotations. My question is this: when we had the PDF, or let's say it's a discrete random variable, I don't even need to say discrete or continuous. I will simply say that the distribution P of X is always, sorry, is always Px. No, the distribution will be P of X equals X for discrete random variables, for discrete X, and for continuous X. Instead of this, I will have some, I will say X is nearly equal to X to keep it simple. Nearly equals to X means that I'm avoiding 0. And I'll divide this by dx, right? This will be my crude way of talking about the distribution. So now I want to know what is the CDF, right? CDF. So the CDF I know for discrete is simply the sum. Before that, I need to remind you that it is simply x less than or equal to x. So it's the sum of all the values of the PMF, right? And because I need x here, so it will be better to use some dummy variable, like say I, and I less than or equal to x. And for continuous, I will have to integrate from minus infinity to x, f of, let's say, t dt. I can use some dummy variable t. Now, this is something you already know. My question now is that how will you express the joint CDF, right? So joint CDF will be one question about x, one question about y. So this small x means that you are looking for values less than or equal to x, and this small y means that you are looking for values of y less than or equal to x. And this will have similar break up. For discrete, it will be double sum f of, you can say ij and ij. You can simply say, okay, I is less than or equal to x and j is less than or equal to y. And for continuous, it would be a double integral. I can use now again dummy variables, let's say t comma s. So it would be dt ds, and t goes from minus infinity to capital X, and this goes from minus infinity to capital Y. So sorry, small x and small y, because I need this x and y at the end. The reason I gave you these formulas is that whenever you have joint PDF or joint PMF or conditional PMF or conditional PDF, you can always turn it to probabilities of any kind, and that should also include the CDF. So you can even now ask another question. What if I am interested in the conditional CDF, right? So capital F, and I want conditional CDF, y given x, so it will be y given x. Now, this is also a probability. So I can first express this as a probability, which is y less than or equal to y, condition on x equals x, and then I just need to remember this thing. this thing. I have to add, yeah, this here we have x, and I actually wrote the other way around. I wrote y. So this will be uh, some conditional conditional PMF over x over all possible values of again you need some dummy variable, yeah. So t less than or equal to x. It's for discrete, and for continuous it will be integral again, um, continuous PDF. So t given x dt, and this is from minus infinity to x. Yeah, so all these formulas, they look different, but they are all manifestations of this simple formula. This should tell you why conditional distribution will be useful. Okay, so let's put all these things into use, and I'm now removing the annotations again. Let's put them to use in this question, example 3.14. I think in the example 3.14 we came to this formula. I'm just writing this for you. You will recall it easily. In example 3.14, we had two random variables x and y, and we came up with the joint distribution which looked something like that. When x, y, and x plus y, when they're all uh, values from this set 0, 1, 2, we had a very nice formula which was two objects picked from 8 objects, and I think x was the number of blue balls and y was the number of red balls. The blue balls could only be picked from 3, the red balls could only be picked from 2, and the remaining green balls, which is 2 minus x minus y, they could only be picked from 3. And otherwise, we learned that this was 0. So this is the starting point, right? This is the starting point of this question. You are given the PMF of a random variable of two random variables, x and y, the joint one. So now you are required to find the conditional distribution of x given y equals 1. First we do that, and then we look for other things. So we are looking for the conditional distribution. He's using actually G here. So he's using G, and to make sure that you also follow how I write it down, I use X. Yeah, because after all, we are looking for the marginal distribution of X, and given 1, right? Given 1, and here it will also be given 1. But 1 of what? Given y. Yeah, so this 1 is the value of y, and this is x, and this is actually x comma 1. So now we need to look for the formula we just saw a while ago. Let me show you what was. No, this was not the conditional one. The conditional formula, I'm just writing it separately. The conditional distribution always have the joint distribution in the numerator and the marginal distribution in the denominator, which for this case will be g, right? So we need this. I think this g will be here in the denominator, right? It will be g of x. Let me show you the main formula so that you don't get confused. This is the main formula, right? The distribution, conditional distribution y given x will have the marginal distribution of x in the denominator and the joint distribution in the numerator. For the conditional distribution of x given y, here we will have the marginal distribution of y in the denominator and the joint distribution in the numerator. So here we are looking for the distribution of x given y. So which of these formulas is relevant for us? Remember, we are looking for the distribution of x given y. So we are looking for this formula. Yeah, x given y. So there it will be x given y. And it means that here it will not be g, but it will be h, because h is the distribution of y. And that is why I also like to write fy. Yeah. So that you know that the denominator has the distribution, marginal distribution of y. But y here is fixed to 1, right? The question says 1, y equals 1. So it means that here we need to fix this to 1. Yeah? And here I will need the joint distribution, right? So x comma y, you will usually write y, but y, we have fixed y to 1. So this will be 1, and this will be 1. So we're not yet done, okay? We only wrote the main formula, which, so now we need two things. We need this thing, and we need this thing. The numerator is easy. Why? Because we have just written the formula for the joint PMF of this question. Yeah? So 3x, 2y, 3, 2 minus x minus y. So let's plug this value y is equal to 1. We need to set y to 1 and we use that formula. So it will be, you say f of x comma 1. I'm now interested in the numerator, right? That will simply be, yeah, we had this 8, 2, and this was x coming from 3. Y in this case is 1, which can only come from 2. And 2 minus x minus y is 1. It can only come from 3. And here the condition, now y has disappeared because y has been replaced with 1. So you have to write, this is the formula when x is a value from this set. It was only 0, 1, or 2, and 0 otherwise. Right? You can simplify this yourself. Actually, this will be 2 and this will be something which will cancel out of this. And this 2 minus 1 is 1, so it's actually 1 minus 6. Yeah, and in fact, this cannot be 2 anymore. Why? Normally we had all the possible values, but here we have this 2 minus x minus 1, which is 1 minus x. So 1 minus x means that this x cannot be 2, otherwise 1 minus x will be minus 1. And minus 1 here will not be allowed. So you can change the limits whenever there are issues. So we are done with this part. Now we'll look for h of 1. H of 1. H of 1. H of 1. To make sure you follow what I'm doing, I'm going to write it in this notation, which is the marginal distribution of y at 1. Now, do you remember the formula for the marginal distribution? The marginal distribution of y, which we also write h of y, is, because you only want the distribution to be for y. So if you recall the law of total probability, you have to get rid of all the values of x. So you have to sum the joint PMF over all the possible values of x. Yeah, all the possible values of x, and the possible values of x are actually 0 to 2. So you just have to add this thing, add this formula from 0 to, so it'll be, you can even, I mean, you can even uh, break it down into separate cases. It will be 0 comma y, 1 comma y, and 2 comma y. And each one of them can easily be simplified from this formula. You have to go with the original formula. You cannot use this formula. You cannot use this formula. Why? Because here we have fixed y to 1. And here we are looking for the distribution of y. So the distribution of y, we cannot fix the value to 1. We need it for 1, 0, and 2. So that's why we want to keep y as a variable. And that's why you need to go to use the original formula, right? If you, I mean, you can just look at all the steps, and at the end you have your uh, conditional distribution. You need to remember the steps. The steps, you need to select one of these formulas. We are using this formula because it's x given y. Then we need to know what is the denominator. The denominator is marginal. So marginal, marginal has to sum over all possible values of x. Why all possible values of x? Why not possible values of y? Because we have fixed the value of y here, and then only x has to be, you have to search over all possible values of x to get rid of it. These are the computations from that formula which I give you here. Okay. Yeah, you. So this was a question for discrete random variables. You can have a similar question for continuous random variable, because we know that this box is not just for discrete, but this is also for continuous. So whether we are looking for conditional distribution of a discrete random variable or continuous random variable, in both cases we'll be using this formula. So let's try it with that question. We are given the joint density in this case, and let's represent this region in 2 dimensions. Okay, how will I plot this region? So it is x, it is y, and x here is less than 1, y is less than 1. So, but x must also be less than y. So you need to respect this as well. And one thing is clear, that you are not going to end up in these 3 coordinates, yeah, because otherwise you are violating this. So the line, this line represents points when x and y are equal, but you want x to be less than y, right? Or in other words, you want y to be greater than x. So we are only looking for this region. Okay, I'm now shading the region. We are only looking for this region, right? So it is only in this region that you will be integrating, right? So if you want the marginal distribution, as in the first part, marginal density g of x, to make sure you know what you are doing, you should replace g of x with fx, because it is for the x, for the random variable x. So you have to integrate over all possible values of y, and because of this region, essentially you have to, because you have to go in the vertical direction. So this lower limit is y is equal to x. So y is equal to x. And the upper limit is 1. Y is equal to 1. Right? And this you have to complete. And when you complete this integration, you get your final answer. And that, because you also have to respect the x-axis conditions. So this will only be true for x between 0 and 1 and 0 otherwise. What he has not written down and what you have to do in every such question is that your answer should be like this, that g of x equals this value, which is 10 third x times 1 minus x cubed, when x is between 0 and 1 and 0 otherwise. Because this 0 otherwise is very important, right? And the marginal distribution of y, in other words, fy of y, in this case, you have to integrate over all the possible values of y, of x, sorry, because you want y at the end. So you have to get rid of all the values of x. And that is only possible when you integrate over all the possible values of x. And now look here, in this region, x goes from 0. Yeah, you have to move from left to right. So the first limit is x is equal to 0, and the second limit is x is equal to 1. Not x is equal to 1. This is the second limit. Yeah, you go from this to this. Yeah. So and on this line, x is equal to 0, and on this line, x is equal to y, right? X is equal to y. So the upper limit is y, and the lower limit is 0, right? This is something which you will recall from multivariable calculus as well. Okay, so you now know the denominators. I'm going back to that formula. We'll be using this formula. And in this formula, you worked out this thing in one, and you worked out this thing in actually in part A. And now you need to divide the joint distribution by these to get your, yeah, he's only asking you for the conditional density f of y given x. So it means that you only need to use this formula, the first one. So it will be f of y given x joint density divided by this one. Yeah, and we just worked it out here. And the joint density you already know from the original question. And you divide, but you must keep in mind that all this nice computation which you can do is only allowed in this region, right? In this region, which means that even in this case, you need those two cases. For this, that's correct, and you will say otherwise 0. For all the distributions, whether it's conditional, whether it's unconditional, whether it's joint, you must have this otherwise case, which will be 0, right? And now let's get rid of the annotation tools and see if we can deal with part B. In part B, you are asked for the probability that the spectrum shifts more than half of the total observations. What is the spectrum here? You know, x. X is the unit temperature change, and y is the proportion of spectrum shift that a certain atomic particle produces. So shift is represented by y, and temperature is represented by x. So this probability is about the spectrum shifts more than half of the total observations. More than half of the total observations. So this will require y to be greater than. What are the total observations? Oh, half of the total observations. Yeah. And remember, y is the proportion. And when you say more than half of the total, so if you divide if the total in the denominator and you say more than half, so this ratio will be greater than half. Although you don't know the exact number of total, but more than half should actually give you enough hint. So because y, the advantage of defining y as a proportion that you don't need to know the actual total. You just say y is greater than half, more than half. And the temperature is increased by how many units? 0.5. So x is 0.25, given that. Yeah. So the probability in part B will be given that x equals 0.25, you will look for y greater than half. And this will require you. Now, this formula, I want you to connect this formula. I'm now bringing it up. We will use either of these two formulas. If it were discrete, we would be using this. If it's continuous, we are using this. So in this case, our question is about P of y greater than half, given that x is equal to 0.25. So the integral will be, first we need to look for the distribution. Which distribution we need? Here it is x given y. We will have y given x, because in our case it is y given x. And instead of integrating over x, because it's a distribution of y after all, you have to integrate over the values of y, and that will be greater than half, means that you have to integrate from 1 over 2 to 1, the highest value, and this question is 1. You can't have more than one value. So it will be, yeah, half to 1. And you just worked out this distribution in part A. Remember, in part A, we did work out this distribution, which I asked you to write down carefully. So this was just a practice question for how do you utilize these conditional distributions into one of these formulas, right? That was it from this chapter. I mean, I only needed to, we didn't need to spend too much time on this chapter, because, and you should also skip the multi-variable cases. We are only responsible for 2 variables in this course. So one thing which is still left before we move on to chapter 4 is this thing. Let me move on. So it's good that I remember it now. So to have a recap, what we learned so far in this chapter, in chapter 3, right? We know that sample space can be mapped by 2 random variables. Yeah, x and y. They will both use different x's, different real x's, and that gives you points in this Cartesian plane. And that gives rise to joint distributions and marginal distributions, g of x and h of y, and conditional distributions, f of y given x and f of x given y. So we know the joint distribution, the marginal distributions of x and y, and the conditional distributions, and these are used to compute any probability of any kind. We can ask probabilities of this kind, and we can even have it either unconditional or conditional on something. That something can either be x given x or y given y. But because we are discussing conditional distribution here, one thing is natural to ask here. When we were in the event space, and by that I mean that when we did not use random variables, so before random variables were introduced, what was our uh, what were the concepts relevant to conditioning? If you remember, we had something called independent events, right? Independent events. So if you say that event A and B are independent, so what that means is that the joint probability of the joint event A intersection B will simply be a product of these two, right? Now this thing can translate. What this also meant is that the conditional probabilities will be the same as the unconditional probabilities. So it doesn't matter whether you condition or not. Similarly, B given A will be the same as P of B. Now this language translates very easily to random variables. So in the random variables, we can now say, okay, that random variable x and y are independent. To be more precise, statistically independent. What do we mean when we say that the two random variables are independent? Independent. Instead of these probabilities, you will now use distribution. So f of x comma y is the joint PMF if x and y are not discrete, and it is the joint BDF it is if x and y are continuous. So if they are independent, it must be that you can uh, factor this into the individual marginal distributions. So it will be g of x and h of x. And in that safe notation, you can always say x comma y is marginal distribution of x and marginal distribution of y. And what this also means is that if they are independent, then this conditional distribution must be the same as the unconditional distribution. And similarly, x given y should also be equal to f of x, the unconditional one, which is the marginal. So I'm just showing you those boxes. Yeah, we are now summarizing that whenever you have two random variables, they will be independent if the distribution can be factored like that, regardless of whether they are continuous or discrete. But this must be true. You need to read the full box for all the possible values of x within the range. So it means that if you want to prove this for a particular pair of variables, you have to prove it for all possible values. But if you want to disprove it, if you want to say that they are not independent, you just need one counter, one bad example. If you can find one bad example where these two are not equal, then you are done. And this is exactly what he has done in example 3.2. He has tried it for this pair of values, and it turns out that this is the joint PMF for these values, and these are the marginal. And if you multiply these two, let's say I multiply 5/14 and 3 over 7, I am not going to get 3/14. So it means that this one bad example is enough to say that x and y. And in that example, 3.14 were not independent. We are skipping these multivariables in this course. And now we are ready to begin the um, expectation as our next topic. So before I introduce expectation, I want you to recall certain calculations from chapter 1. So let's go back to statistical theory, right? I told you the distinction between probability theory and statistical theory. Statistical theory, and there we learned something which we call the sample mean. Sample mean x bar, and if you remember, the formula for that was simply add all the values in the data set and the sample and divide by n, the number of values. This was the usual formula, but I told you that a much more interesting formula can arise if you use x1, x2 not for values in the data set, but for unique values. So if you look at the table, if you have a frequency table and you have to look for unique values, so that they don't repeat, and then you can have say that okay, x1, x2 are the unique values, and here I will have a column of frequency. So I will say that okay, so this is value. This x1, let's say, appears f1 times. This f1 is now the frequency. Yeah? It's not the PDF or PMF. Let's say this x2 appears f3 times. This x3 appears f3 times, and so on. So then you have to replace this formula, because you cannot now say x1 plus x2 plus x3, because these are only unique values, right? Let's say there are n possible values. So you have to multiply each value by the frequency, because this unique value will be added f1 times, because the dataset has that number of repetitions, f2 and f fn. This is what we learned in that chapter, and the denominator will simply be the number of all values in the table, which is f1 plus f2 plus fn. Yeah, all the frequencies. And we also learned that a better way of writing this is the summation over all possible values. And one last step, I also told you to think of it in a different way. That instead of dividing this at once, you divide them separately, right? So if I divide each value, sorry, each frequency by, sorry, this is fn, by the sum of frequencies, which is the number of data points. Sum of frequencies, sum of frequencies. So these are now relative frequencies, relative frequency R1, R2, Rn. So if I now summarize the calculation of the sample mean, I can simply go with the unique values and I multiply each one by the relative frequency. Relative frequency. And now this is where we can connect this concept to probability theory. In probability theory, these relative frequencies in the limit, when we have large numbers of data sets, they are replaced by probabilities. This is one of the interpretation of probability. And for discrete random variable, that will be our PMF. And for continuous random variable, that will be something related to PDF. So it means that now I can come up with a new formula. Instead of looking at a sample, I'll be looking at a random variable x, and that random variable, now these small x is a possible value of that random variable. And if I use this motivation, I can now construct a formula where I sum over all possible values of x, and each x is multiplied by the corresponding PMF. I'm using the exact same computation, but changing the meaning of relative frequency to probability. And this is something which is a property of x, because I'm doing it for the random variable x. So it is called the expected value of x. And people also call it the mean. Remember, it is not sample mean, it's just the mean. And by just the mean, we mean population mean. I told you sample and population in the first chapter. So population mean is for the entire population. Expected value of X is another way of saying the same thing. But the computation here is only looking for possible values and the PDF or the PMF. And PMF comes from theory, right? It doesn't come from data set. So we can now get back to the chapter. And this is now our final definition of the mean of a random variable. You can read this yourself because this is exactly what I told you. Instead of using fixed numerical values, I gave you a general picture, and the mean of a random variable. You can also call it the mean of the probability distribution or the expected value of the random variable. There are different ways of saying the same thing. Expected value of X, mean of the distribution, mean of X, and we can simply write it E of X. E is for the expected value, and this will be the formula. Yeah, multiply each possible value of X with the corresponding PMF and add over all possible values. And if it is discrete, if it is continuous, it is obvious that you multiply each value with the PDF, but because PDF is not a probability, so you multiply by dx and then integrate over all possible values of X. Let's see how to apply these two formulas in an actual question. So let's say I have this question, which is a lot containing 7 components is sampled by a quality inspector, right? The lot contains 4 good components and 3 defective components. So let's say there is this lot or box, and in that box I have 4 good components, G for good, and 3 bad components or defective, D for defective. And in total I have 7 components, right? And what does the inspector do? He draws a sample of 3. So you are just drawing a sample. Draw 3 components at random, right? How do we know if this is by replacement, with replacements, ordered, unordered? That will be determined by the question being asked. Find expected value of the number of good components in this sample. So the random variable here, X, is the number of good components in the sample of 3, right? In the sample of 3. And now I want to find this expected value before doing any experiment. So it's not a statistical question, it's a probability question. So first we need to see the formula. First we need to know all the possible values of X, and then we will get to the PMF. So what are the possible values of X? Can anyone guess in this case? If X is the number of good components, what are the possible values? So I can say that X belongs to, in this question, X belongs to which possible values? 0 would mean no component is good, right? 1 would mean 1, 2, and 3, and you cannot go beyond 3. You cannot have 4 good components. Wait, in the number of good
बारिश करा दी है
yeah, so it will be 4 as well.
बारिश करा दी है
Yeah.
ना ऊपर ठीक है
You should actually you should switch off your mic, okay? Whoever is there.
मार रखते हैं और उनकी एक्यूरेसी इतनी है कि 2000 किलोमीटर दूर से वो मोबाइल मारे तो वो ये कह सकते हैं कि
Whose mic is on?
कमरे और एन मुमकिन है मैं ये कह रहा हूँ ये
You need to
सच्चा
turn
साबित
your mic off. Okay. And if I hear anyone again, it will not be good for you. Okay. You need to remember the etiquettes of sitting in this class, right? So the possible values are, although there are 4 components in the lot, but he is only drawing 3 components for inspection. So yeah, it cannot be more than 3. And the distribution is very simple. For the distribution, you already know that I can write it on the next page. So the PMF of this random variable will be, you need the sample size, the size of the sample space, which is 3 components drawn from 7, and X good components, because X is the number of good components, right? They can only be selected from 4, and the bad components, which is 3 minus X, because 3 is in the lot, 3 are selected from the lot. So 3 minus X will be bad components, and they can only be brought from 3 components. This will be the case when X belongs to 0, 1, 2, 3, and otherwise it will be 0. Otherwise it will be 0, right? Now you have everything. So now all you need to do is to find the sample mean, which is the expected value of X, expected number of good components. So the formula goes like this, all possible values. And in this case, the possible values are 0 times f of 1, because you see 0, f of 0, sorry, f of 0, 1 times f of 1, 2 times f of 2, and 3 times f of 3. And this computation you can do yourself. Yeah, you have this formula, you just plug f is equal to 0, x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3, and then you set this. The thing you need to realize is that you are computing the number of, he has done it for you, okay, in the example. You can try it yourself. 1.7 is the expected number of good components, and you are doing this without doing any experiments, without doing and collecting any data. You are just using the model. So this is your model, right? I told you that in probability theory you will be using a model, but in statistical theory you will be using data set. Okay, the next question for the for getting some practice of expected values is this probability problem. So a salesperson for a medical device company has 2 appointments. So let's say you have appointment 1 and appointment 2, AP1 and AP2. At the first appointment, he believes he has a 70% chance to make the deal, from which he can earn 1,000 commission if successful. So in the first appointment, he has 0.7 probability, right? 70% chance of having a deal. And when he has the deal, he can earn $1,000. 0.3 is the probability that he's not successful in the deal. And when that happens, he does not get any commission, right? 0. In the second deal, in the second appointment, he has a 40% chance of getting the deal, and 0.6 is the probability, which is 60% of not getting it. So if he doesn't get any commission, but if he's successful in the second appointment, he can get a commission of 1,500. So there are now 4 possible cases, yeah. And he's asking you for the expected. This is the thing which you need to read. What is the expected commission based on his probability belief? So he has 2 appointments, and from these 2 appointments, we are going to see how we are going to define a random variable x, which is the commission and dollars. So what are the possible values of x? Why am I asking for possible values? Because I'll be ultimately using this formula, and this formula requires possible values. So one possible value is that he gets no commission because both the deals are broken, right? So 0 is 1. I can say x belongs to one possible value is 0 when none of the deal works for him. 1000 is a possible value if only the first deal is successful and the second is not successful. 1500 is 15,000, sorry. 15,000, no, 1500. 1500. 1500 is the commission if only the second is successful but the first one is lost. And if he wins both the deals, then he gets both these amounts and this will be 2500, right? And the next thing is to find the PMF. And he is giving you a hint, assume that the appointment results are independent of each other. So what is the PMF of 0, f of 0? Who can guess that? So independent means that both these events are independent. So he will get 0 commission in this case and in this case. So you just multiply these probabilities, 0.3 times 0.6. That is the PMF. What will be the PMF at 1000? So he gets this much commission when this is the event in the first stage, and he must not get anything in the second stage. So he multiplies these two probabilities, 0.7 times 0.6. And same goes for f of 1500. 1500 is when he gets this, but he doesn't get this. So actually he gets 0 from this. So he multiplies 0.3 with 0.4, 0.3 with 0.4. And the last one, 2500, when he wins both the deals, so you multiply 0.7 with 0.4. All the probabilities have been calculated for you here. Yeah? For 0, these probabilities, for 25, these probabilities, both are successful. In this case, only one is successful, the other fails. And in this case, the second one is successful, the first one fails. And then you just combine all these PMFs with the values. Yeah, so x times f of x, and then you add. So this is x, 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 and this is f of x, f of x, f of x, f of x, and you get the final value, right? Write P in the chat window before I close the meeting, right? And if there are questions, we have 1 minute for questions.